So welcome everybody to the new session of NTech. It's about, as you know, Risc-V. We don't say Risc-V. There's nothing to do with Sputnik. It's a processor. Our speakers today are myself, Olivier, and Benoit Calbot, who are both executive at Nalys. And I will start with a slide presentation about Nalys, very short, about us. As you may know, we are software consulting company dealing with the management of new technology. Our main asset is to provide companies with the best practice and the know-how on how to leverage on new innovation and technology, so to keep process and new products up to our customers' expectation and dealing with the management of the total cost of ownership of the technology. So we are gathering a lot of experts, as known as executive. I will be back on this. A few figures about Nalys. Nalys has just turned 10 years, so it's not a new company, but a mature company about technologies, gathering 2,050, I'm sorry, 60 people and counting, luckily, gathering to 22 million euros last year, covering 3 domains, maybe 4, and a few countries, mainly France and Belgium and France, and we are conquering, if I may say, Great Britain and Italy. Let's see that next year. We have over 70 customers, and you may see, covering 3 domains, which are life science. Let's say it's about pharmaceutical industries, medical devices, technology, as you can read, software. We call it an innovative software division, and energy. And I will focus on innovative software, which Benoit and I are part of, covering defense, telecom, telecommunications, transportations, and let's say Internet of Things, which means mainly embedded software consulting. What are executive? Very short introduction of executive. The executive in Nalys are the experts and dealers about new technologies. We are permanently backing up our consultants at the customer's place to make sure that everything's okay, and the consultants can have the best advice or best practices managed and handled at customer's place. Moreover, each consultant at Nalys is always, as well, is backed up on the career point of view, okay, and project point of view. So we have many people around the consultants. It's very different from usual consulting company. So if you want to join us, now you know. So it was about Nalys. Let's talk about the Risc-V, future of processor, or is it a new thing that is very upcoming at the moment? Is it a new processor? I would say definitely not, because it's, first of all, a specification. New computer, no, not exactly. It's more processor, and it's a competitor to ARM and Intel, as we may know at the moment, maybe. To be very honest, we all deal for many years with Intel, present in all PCs and many embedded devices, less unembedded. And ARM, as you may know, because we have ARM in smartphones and everywhere, and from microcontroller to CPU, very power intensive or computation intensive devices. But Risc-V is an alternative, a new alternative that may be very interesting for many industries and chip makers. We'll see. It's not only a concept. We'll see. As you see, it's also actual hardware. You can buy some device development board and a real industrial board for projects. So what it is exactly? Risc-V, and 5 stands for the 5th generation of the definition of Risc. Risc-V is, first of all, a foundation with 200 members and counting. Sorry, my cat is bothering me. And formally created at Berkeley University in California, where they define processes and everything about processes from theory to practical processor from the early 80s. So it's 40 years old as a concept. And they have recently decided to move from United States to Switzerland, certainly for jurisdictional issues. Risc-V defines an open source instruction set architecture. What it means, we'll come to this a little bit later. It's based on a Risc. We'll come on the definition later on, but it allows chip makers to build processor on their own without any dependencies. That's very interesting regarding this. I'll let Benoit introduce what the instruction set architectures is.
So what's an instruction set architecture, or in short, ISA? That's the command language, more definition of protocol or API for software people between the hardware of the processors and the software operating system and applications. So when you see on these slides, you start from silicon, you put transistor on it, transistors makes logic gates, functional blocks, that's called microarchitecture. And all of that is seen from the software as an instruction set architecture. So on top of that, yeah, you have the compiled code, which use that instruction set, so the binary code. Yeah, you can go.
Sorry.
Yeah. Go further. So the main point inside the processor, inside the hardware, which deals with the ISA, is at the decode phase. Here, what you are seeing, it's a typical pipeline, and that's the pipeline, the 5-stage pipeline for the Risc-V. So for one of the implementation of Risc-V. So you see the first one, that's the fetch, that's just taking the instruction from memory, and the second step is the decoding. So decoding is transforming the instruction, the bits that define the instruction, into something that can be used by the hardware. So into digital signals that will be sent to the different functional blocks. And afterwards, you have the real hardware execution with the issue, load, store, execute, right? I won't go more in detail. That's more for a specific processor design presentation. So now we can go to the next slide. So what's a Risc? We start to talk about that. That stands for Reduced Instruction Set Computer. What's reduced instruction set? That's basically you have few compared to other technologies, to the CISC that we'll see later on. Few instructions. So instead of, for example, for an Intel processor to have 15 pages of instructions, you have only 4 for the Risc-V, which is around 120, less than 120 instructions for the full processors. Most instructions execute in one instruction cycle, so that allows you to have very fast instructions. So if you Risc processor is running at 3 gigahertz, normally it will execute 3 giga instructions. So depending on how you count them, it's in MIPS or in flops. Flop stands for floating point instructions. And so, like I said, fewer instructions compared to the CISC. And most of the Risc processors are pipeline. You just saw in the previous slides what's a pipeline. Again, I won't go into a detail. And that's yeah. You can go further. So the CISC so complex instruction set that's really stand for a complex instructions. So compared to a Risc, so the scope of a Risc instructions is very limited. So basically, take one instruction from register A, a second value from register B, add them together, put that in register C. In a CISC processor can go, okay, take the data from the memory, add it, or perform, like I said here, as an example, an FFT, and put that back into memory, which requires a lot more cycles. So for each instruction, you can have spent a lot of cycles. So instead of having 3 giga instructions per for a processor running at 3 gigahertz, you can have maybe 300,000 in the worst case. And also the decoding hardware for it's really, really complex because one instructions can imply a lot of steps for more than few hundred steps in the worst case. And a good example of it, and Intel 86, and for older people, the VAX, so really older generation system. So a little bit of history, because I just took a really snapshot of about it. In the early design, you didn't have the concept of instruction. You simply add 1 and 0 that you put directly into the processors, and you were reading the results on LAMP. If you want to look for things like that, look for a PDP computer mainframes, you will have a good example of it. Afterwards, in the 60s, they say, okay, that's not possible. It doesn't scale up. So they designed the first CISC processors. There, the idea is that we are unable to build the compilers that didn't exist at the time. So the hardware has to do everything. So the decoding part of the processors were really complex. And a simple example, the first computers were computing in a BCD, so binary coded decimal instead of binary, which made the computation really, really complex. Afterwards, they say, okay, no, that's not scaling up. Let's do it in another way. The first integrated circuits appeared, and so the first microprocessor appeared. So that was the Intel 4004 that was made for small calculators. I mean, small. That's a calculator that you can have in your watch. And also at the same time, the first compilers appeared. So that means that the complexity of the decoding part of the processor could be lower. So the first microprocessor were really simple, a few 1,000 or 10,000 gates. And now, if you think the latest processor have more than 10 billion gates. Again, with the history, it was very successful. You are still using the x86 processors, first computers, but again, it was not scaling up. The speed of the processor was not was staying relatively slow. So in the 80s, there was another idea that appeared as the Risc that we just talked about. So basically, get rid of all the complexity of the decoding and do it in software, so in the compiler, and just have a very simple Risc processor. And that's what we are talking now about with the Risc-V. History didn't research didn't stand still, and further on you have trials, processors that are existing that are very long instruction words and epic, so explicit parallelism. So those processors put the limit again further, allowing you to execute either more instructions per clock cycles, or in the case of the epic, just letting the compiler deal with all the complexity of organizing the instructions to keep the execution as efficient as possible. But that's for later. And you have also to keep in mind that Risc processors borrowed a lot of techniques from those processors. So, yeah, I already discussed about the complexity. So the fight between Risc and Cisc. That's make it simple. Risc is simple and fast hardware. For complex behavior, yeah, you have a lot of instructions. The compiler is more complex, and for some tasks, it can be slower compared to Cisc, because Cisc can be optimized to do complex things like rendering, performing encryption when you have the full algorithm running as one instruction. That's nowadays that's put as extension in Risc, but the core idea of Risc is not to do that, because complex instruction takes more time. So the Cisc, yeah, that's the the opposite. So yeah, complex and so slow hardware, but simpler compiler. But it doesn't scale with complexity. So that's why your 86 computers processor nowadays, it's basically a Cisc processor that Risc processor that just have a front end that looks like a Cisc processor. Yeah. So now, what's really a processor? We discussed about instruction set and a lot of things, but really not what's really a processor. From the first one of the first slides I shown, that's the defined by the instruction sets. The technology that was not highlighted, but for example, we are talking about 22 nanometers, 10 nanometers, 7, 5 nanometers. And so it means smaller processors are faster, consume less energy, more efficient. A good example is the new M1 processor from Apple. That's say that basically it's twice as more performant than the Intel processors. Won't go further in there because there's a lot of marketing. But for the processor, this means also that you had also a clock. Most of the processors are what we call synchronous processors. So there is a clock, that's the heartbeat of the processor. But you have also memory, because you have to store the data you are working with, and also data buses, because that's you need to move data around. A processor is not more than that. Now you have also what's we call an MCU, so a microcontroller. So that's a processor plus a lot of peripherals like memory controllers. When I talk here about memory controller, it's for example your DDR4 controller that can be put directly inside the processor, with most microcontrollers also together with the memory itself, but also things like timers, GPIO, so IOs for the processors, E2C, so UARTs, all of extra peripherals that are useful to interact with the outside world. And the next step is the system on chip and the FPGA approach. So the system on chip push basically the idea further by integrating basically nearly all that you can find on your motherboards inside one chip. So it means the RAM, the flash, so the long-term storage, but can be also power management and other peripherals. So you can make a full computers on one chip. And by the way, what you saw in what's the first slides about the Risc-V in the Arduino format, it's a system on chip. And another approach that's often nowadays linked with system on chip is the FPGA. So you can also put programmable logic in it. So you can have an IC, I will say it's more general than a processor, but call it a processor if you want, with on it what we call Art IP. So that's really the programmed silicon, so the micro architecture implementation of the processor, but also of peripherals like Ethernet controller, just burned in silicon, and also what we call soft IPs. So that's programmed peripherals or processor, but in an FPGA. And FPGA is a field programmable gate array. So it's just an array of gates that you can say, okay, I connect that gate to that other gates to implement a functional block. And that's is really useful to program extension or to prototype processors, because basically, if you have a very good idea to make it faster or to implement an extension, you just have to program it like you would program a microprocessor on your PC. So as a summary will be very quick. Risc-V, so it's a RISC-based ISA that can be implemented either on FPGA or silicon. Give example of that at the end of the presentation. And it can be present in a more complex system that's are called system on chip. The ISA itself is really modular. There's a base plus extensions. We'll see that just later on. And it's really scalable from a small microcontroller running a few tens of megahertz up to server-grade multi-core CPUs that are really able to do exactly the same as Intel-based server or ARM-based server. And it's open source, at least the ISA is open source, and also a few reference implementations. So you can perform security audits on it. So you really can know what's in it, and you don't have to blindly trust companies like Intel, AMD, or even ARM to know what's in it. So it can, for defense, it's a very big added value. So now let's talk about the instruction set.
Yes, I take on this.
Yeah, take on that one.
So as Benoit explained, we know all about CPU from MCU to CPU, and Risc-V is specification about sort of processor, especially instruction set, and they all, since they learn from what the past, as I said, it's the 40 years ago approach on theory or about CPU. define from the ground up what can be a processor, what can be an instruction set architecture. And so they took into account of all we know about this. So there is no legacy issues about the processor. So they directly introduced 32 for 64 and 128-bit architecture from the ground up, from the very beginning. And then you have gradually some extension of capabilities, which comes obviously from integers computation only, then floating points and vectors, now also known as single instruction and multiple data computation. And it allows extensibility of the instruction set and the processor in itself with secret bits and secret instructions, and also foundation sponsored, which means that they are collecting ideas or definition, let's say from members of the foundation, and create a new definition of instruction set. So adding, for instance, matrix computation, complex numbers, and also digital signal processing computation. So the processor in itself doesn't do everything, but can do from simple thing and gradually adding some capabilities and extensions. So given this complexity of possibilities, they have a naming convention of the Risc-V processors. When you buy a board, you have to look up the small name of the processor capabilities, which always begin with RV or R5, whatever. Then following the bit architecture, then you have either integer only operation or embedded variant, which is integer operation limited to 16 processors. It's really designed for microcontroller use, and like we may know in an embedded system, hence the E for embedded system. Then you have in this exact order, that's very funny to define the exact order of the options and extensions that are sponsored by the foundation at the moment, which begins with multiplication division, which are not included on the base definition. It's only adding and subtraction, which is, however, the same. Then you have atomic instruction, etc. You have a huge list. And so you can have a Risc-V, which is RV32, I and MFD, it's an example, or what the capabilities of the processor. They just grouped the very, very common definition of integer plus multiplication division to a single G definition for the processor. You will often see RV32 GC processor at the moment, which means what I said just before, plus compressed instruction for memory consumption issues. I'll let Benoit introduce a little bit, and we will not cover in detail the instruction set, but fast overview.
No, that's not the purpose to go really in the detail, but you can already see that the instructions are grouped into different templates of instructions. With the part here at the right, that's the opcode that allows the processor to decode quickly the instruction and to know what he has to do with the rest of the bits, which are really important. For example, to say, okay, I want to use a register-specific register, or to say, okay, I add a constant to a register, and you can put that value directly into the instructions. So you have, like we already discussed a little bit, basic instructions like I load data from memory inside a register, or I store that in that. I jump, I do arithmetics, plus, minus, or logical operations. So what's the job of what's called an ALU, arithmetic logic unit. But you have also privileged instructions. In the privileged instructions, you can really have a feeling of it when you are programming with semaphore, for example, or atomics. So you can see, thanks, here the privilege instruction, like you can see what's used mostly for a semaphore and also for hypervisor. So you can also, that's what's called traps for processors, is that a processor can encounter an instruction that tells him, okay, either I don't know that instruction is unknown, so it's cause an exception to the processors, which is cause directly a trap to specific, it's an interrupt to specific address that's used by supervisors to emulate instructions. So for example, for security reasons, but you can also have instructions that do a direct request to go in to an hypervisor trap. Basically, thing that's about like an onion with different layers, and each layer has another level of security from the lowest to the highest, and those trap and also the change level instruction can tell the processor change your level or your mode of working. And also, yeah, you have interrupts and things like that. It's also more specific. Like I said, the ISA for the Risc-V defines three levels. A machine mode, that's the first one that's is used, so at reset or boot. You can go into a user mode and to a supervisor mode. So the user mode is your user application or your operating system, and the supervisor mode is more for hypervisor or some OS that using that also.
Let me interrupt on this one. The supervisor is more the kernel level. Machine mode is very the minimum that you have to implement in a Risc-V processor, and it's at very beginning. You have the reset and the boot and the level that you can manage. It's single, I would say, clock settings and part of the very low level of the processor. And then the supervisor mode is usually what runs inside the kernel. And user mode, it's usually what runs in an application mode. As you have seen, the Risc-Vs are from MCU, microcontroller, to CPU. A microcontroller that doesn't have necessarily the supervisor and the user mode, but the machine mode is of course mandatory, and interrupts happen in machine mode levels. It allows hierarchical code execution like we require for operating system and general operating system. So it gives us a large number of possibilities for execution and scaling up from microcontrollers to general purpose operating system. As pretty much like the ARM, everything is memory mapped actually. So you don't have specific instruction to allow dealing with input or output like Intel or Spark processor for people who know about Spark. Everything is about an address, and in the address, meaning that you control the hardware or the register below it. So it's very simple. Since it's very simple, you may imagine that an application can do anything, but we have obviously to manage the memory and the access to memory, and every register or peripheral control in the CPU. So they all already introduced the equivalent and then the memory management unit, which is absolutely needed for operating system, allowing paging. So the memory is completely visible at the supervisor and of course the machine mode level, but it's partially in linear way seen in the user mode, which means the application. Of course, you have limited span of the memory addressing, but it's sufficient for most of the general purpose application mode. And it allows to switch from a process to another. And I'm not talking about threads, because threads see the same memory layout. But for processes, you have to switch from an environment to another environment. It's already included in the Risc-V view. And calling convention, which you may know, also known as application binary interface API, they already defined specific registers for specific use. For instance, the XO is always 0, X1 is the return address, etc., etc., etc. So you don't do everything you want with the registers. It's always built in the conventions. So why create the Risc-V? Up to now, all CPUs were more or less licensed. That it depend on the cost of on the recurring royalties. You have to pay royalties to use the CPU for now. There are exceptions, especially for microcontrollers, like the Italian AVR architecture, which is open source and license free. But by the way, open source doesn't mean license free. Open source means that you can see everything, but you are not necessarily allowed to use it as you want. You may have to license something. It's very tricky and very confusing. And proprietary system doesn't allow the research easily. Especially Berkeley was very concerned about the background of this, and they have a very good background from the beginning, and the early 80s about CPU. That's the key, the turning point of this. Actually, the cornerstone of the Risc and the Risc-V philosophy is to keep it open and keep it widely accessible for everything, to put new technology or new theory into this. So, and as I said, they start from the ground up. So they learn from the past lesson, and you don't have to deal with the legacy like the Intel processor. As we said, there is no license cost. ARM, as it's written, it's huge revenue for them. They have licensed the technology to more than 200 companies, I think, chip makers, and it's a huge revenue. You may say that, okay, but Risc-V, how do they live? They live on just the members, what we say, the members of the foundation, to put the money to put in it. That's all. And it's theory. Then you have to back up your technology in the production on your way. It brings independence. It's very important. You do not depend on anything, not even a license. So it brings naturally the sovereignty. It means that you can deal with all the process of manufacturing the CPU and dealing and selling the technology. And as it's in the notice, independence in sovereignty are the primary concern for defense and military. That not only, if you remember the Huawei issues, because Huawei has lost the Google Android license, and they may lost the ARM license as well if ARM is taken over by NVIDIA, which is not done yet. So we'll see next February about this, because the European community has something to say about this. But it's very, very at risk at the moment, and we have a huge problem of dependency about, especially the Americans. They are allied, I know, but there are competitors as well. A few reference on the internet, you can check this out later. About chipmakers, I'll let Benoit introduce a few chipmakers we have at the moment.
So as you may expect from what Olivier just said, a lot of chip makers using Risc-Vs are Chinese ones, because they have the issue about the licensing US controlled technology. So one that's very well known, it's Expressive, which is making a small communication processor, so Bluetooth, Wi-Fi modules called the ESP32C3. They have a few a broad range, let's say, a broad range of microcontroller systems. Some of them are ARM-based, and now with that one, they are starting to have Risc-V based processors. Another one that's probably better known to people that are using SBC, so small board computers, is Allwinner, which is a huge range of ARM-based processors, and now also a new product line of Risc-V-based processor. This you can see the C906, which is one of the Risc-V implementation that's more processor, typical desktop processor like Risc-V implementation. Also, a new one that you will have the link, you can find it back really easily, is TN. That's an Alibaba company, which is also making a new range of Risc-V cores and even boards. And this technology, which is the last one, it's a founding member of the Risc-V Foundation, which is also making processors. And this technology is more an IP company, so with intellectual property, which is sublicensing its implementation of Risc-V and other processors. In the US, you have a Sci-Fi, which is one of also a founding member of the Risc-V Foundation, and that has a wide range of processors and boards. It's basically the maker of the reference boards for the Risc-V, which is i5 boards. You can find them, by the way, on crowdsupply.com, which is a crowdfunding platform for electronics products. And in Europe, you have Codasip, which also founding member. And again, Codasip is more an IP-based company, so sublicensing implementation. So there are others that are involved, but either in a more specialized field like microchip with this FPGA-based development board, so on which you can run soft core implementation of the RISC processors. A Belgian company called Silex Insight that works more on security aspects of the implementation together with Andes technology. And also, that's more in stealth mode at the moment, NXP and ST Microelectronics, again, both European companies that are working on Risc-V products, but there is no official announced so far. Now, to the software tooling. So a processor is nothing without software running on it. So you have several ways of doing test of experimenting with it. Is either what's it's called the simulator. Simulator is basically a program that's running on your processor that interprets the code, an executable that was built for the Risc-V, but on your either ARM based system or on your x86 or your desktop PC. And that can be either functional simulator, so it's a test the function, so it's not accurate according to the clock, or the one that's exactly clock accurate, so like exact step, which is written, by the way, in C++. Or you can say, okay, I have, for example, the PolarFire from Microchip board, and I just want to put the Risc-V on it. and so you can go, yeah, I go to GitHub, Risc-V, I take the implementation and I put on my FPGA board, and from that one, you have an hardware Risc-V processor, Risc-V board that's up and running. Or you can use QEMU, which is widely known, widely used, and there you can test like a virtual machine on your PC. It's not exactly the same as a simulator, but that's more specific. You have obviously all the GNU toolchain, which was adapted for Risc-V. So you can find support for common Risc-V implementation with a specific implementation for example, the TIET processor when you have the link with it. So you can have Linux, Android, your build root, QEMU, bootloader, so U-booter, fully available for you to use. You can also use the LLVM or CLang for those who prefer that to the typical GNU tool chains, without the advantage of being more focused for optimization and analysis of the code, so that can generate, like I say, for example, Risc-V vector instructions. So, like I said, Linux is of course supported. That's one of the first targets, but also real-time operating system like Zephyr, or the well-known free RTOS, which is free, and it's real-time operating system that's more geared for microcontroller. And also that's quite new, it's an OS implementation done in Rust. So Rust, for those quickly, for those who don't know Rust is like 2020 remake of C++, with a lot of safety measure built in the language itself, so you can avoid troubles with, for example, issues with buffer overflows, or with threading issues. That's put inside the Rust language.
So in conclusion,
yeah,
we'll try to keep a few minutes at the end for the Q&A session. Well, we talked a lot, but it's a very fascinating subject. In the news, you have a few recent news, because it's very recent, about Risc-V. So it's, as I said, recently, only 2015, so 6 years ago, with the creation of the foundation, and everything's, yeah, that's so Risc-V is surging at the moment. It's very present if you are aware of the embedded system, and if you are aware of the processor. It will be huge in the next years. We have also a few news about the trade-off about frequency and power, and recent researchers has reached very few watts per instruction, and it's very so for low power CPU, there are a huge field of application. It's very promising. Alibaba has just announced, as Benoit said, the Risc-V toolchain. It's open source. Cypher has already delivered dev boards and development boards. Very interesting. They were very expensive at the moment. It's very interesting, and it's very new announcement. Europe is pushing Risc-V for what we knew as HPC. It's highly parallel computation for data centers, and they put a lot on it. So it's very interesting. So only 10 years after the foundation, we are at a turning point. Big actors will put an enormous effort in the embedded system, and as we said, that it's independence and sovereignty issue. It's very important for industrial as chip makers and users to become more independent from the US or even Japan with whatever, or Asia, not at chip makers, but also. Development boards have become cheaper and cheaper. As we see, it was $1,000 for the beginning, and now it's as much as $200 or $200 dollars. And you can recently find the famous ESP32 from Espressif, which was based on tensilic CPUs, and they have totally changed their market to turn into the Risc-V market and make it pin-to-pin compatible processor. And it's under $5 at the moment. If you want to buy some on AliExpress, it's very simple to have the processor and to get your hands on it. It's very, very interesting. There are microcontrollers, and you have Winner Macro just announced the Huantie, which is from I think Alibaba. It's approximately $2. It's very interesting. So I talked about the data sensor. So shape the future. So as Benoit already said, it's now at the moment, and it's now to jump in the bandwagon of the Risc-V. So I will end the session with this. Thank you, Benoit, for this as well. We are ready to listen to your questions if you have any at the moment.
If I may.
Sure.
Yeah.
So we've talked about a lot about what there is in Risc-V, but what do you find that isn't there and wish were there? What is missing?
That's a good question. It's very comparable to, as we said, from ARM and to x86. Actually, what is missing is what you can provide. Since it's open, everything that you miss at the moment will be brought by a member of the foundation or another company. It's open. So what you miss in a Risc-V is what you can bring, actually. It's like open source. If you are not happy with something, you can do it yourself. Okay, it's not about waiting for someone to do the job for you. So you can collaborate. It's very interesting for this. And since the Asians, especially the Chinese, are very prolific in this, they can provide a new solution. And as we saw, we already see new instruction for SIMD or vector operation in the matrix. So it's getting bigger and bigger. You may say that it can be complex in the future, and we can deal with legacy. That hence the capabilities you put in the Risc-V definition at the very beginning. I hope I answered the question.
No, I can on top of that. You have to know that was not really highlighted in the presentation, but the first building the hardware is a really complex and expensive task and slow task. Don't forget that the ARM, for example, exists for, since I don't remember exactly, but around 84 or something. It's quite, so it's quite really old technology. So it took really a lot of time to become mature for the ecosystem of computing to be accepted as a good solution. So it will take also time for the Risc-V. That's totally normal. We see, for example, with companies like Western Digital and the other one I don't remember. That's they are using the Risc-V in 50% of their hard drive controllers. So in only a few years compared to what happened with ARM. So that's going faster, but you still need time. when you are making like you could see that's on the slides about ARM. ARM is making not itself, but billions of chip a year before all companies commit themselves on Risc-V to build as much chip. You will need time and also a huge library of compiled and validated software on the Risc-V. For example, and that's the best example, in HPC, we discussed quickly about that. They are still using mostly x86 processors because basically all the libraries for x86 is well understood and working well. Even ARM system in supercomputers doesn't have the same level of it's not really maturity, but people don't have the same level of experience with ARM. So people are really conservative because if something goes wrong, you lose a lot of time and a lot of efforts, and nobody can take the risk. So basically, the main thing that's lacking now for Risc-V is time. And that's what we will see in the future. But for everything else, like Olivier said, you can add extensions. All high performance extensions are coming to the Risc-V. So there is nothing really lacking. Even GPU is coming up with the new Risc-V implementation. So you won't have directly latest NVIDIA GPU or AMD GPU core into your Risc-V because you have the same licensing issue that's with ARM, but that's just a matter of time.
Yeah, it's a matter of time to true. And another question which is interesting from Benjamin, I like Benjamin question. So, does this new tech could have an impact on the semiconductor shortage that we see nowadays around the globe? It may not solve the current shortage, but it may definitely be a workaround for future shortage. Since there is no license growth, it will allow a lot of other chip makers, from small chip makers to bigger ones, to provide chips. And well, really awaiting for new chip makers, especially in Europe, for this. So that will be a solution for this. Yes, definitely. Thank you for the question, and thank you for Loic's question as well. Okay, so thank you everyone for attending this session. Thank you very much, Benoit, as well, and for the directing the session. So we hope to see you.
Thank you for the presentation.
You're welcome. You're very welcome. So see you in the next session next time.